why are we here talking about this? Why are we talking about retrofit heat pumps? Right? What's up with retrofit heat pumps? And specifically, this is retrofitting heat pumps in place of a gas furnace or an oil furnace, something like that. Typically, a forced air heating system where the fuel-fired heating is going to be removed, and we're going to put in a heat pump to provide the primary heat source in the house, or at least a serious majority of the heat in the house. So that's why we're talking about this. I have done this presentation or something very similar to it. This one's actually a little bit extended. We added some things in here. And I've done this presentation at a number of different conferences, and a lot of people were requesting, saying, hey, do you have a recording of this? I'd love to see this. Where can I watch it? So we just decided to do it live online and put it out there for everybody, try to get as much information out there to the various trades that we can. So that's why we're here tonight. So we're talking about, realistically, when we're replacing these appliances, we want to keep people comfortable. This is why we put in heating. We're going to use electricity to provide heat to a house. We want to keep everybody nice and cozy, snug and warm in their houses. That's the goal. So let's talk about how to do that. Remember, we're going from a gas or an oil-fired appliance. One pathway to go with this is what's called dual fuel, where we keep that fuel-fired appliance, or maybe put a different fuel-fired appliance in, and we stack a heat pump with that. And we use them, one or the other, to provide heat, right? The other pathway coming from a straight fuel-fired appliance for heating is we go 100% electric, and we do a heat pump. And if it is a cold enough environment where the heat pump or the heat pump is such that it cannot provide heat to the house 100% of the time, we may supplement that with a little bit of electric resistance heat. We're going to talk about some of that tonight too. And realistically, a lot of things I'm going to talk about in here is stuff that I've learned over the years, whether from being in the field and actually experiencing these things, or taking classes, learning from other people in the industry, and put all this together in one spot. So, in order to be successful in this process, one of the first things we need is knowledge. Now, we have a lot of knowledge, but we need a little bit more to be very successful in this process, right? And that knowledge comes from occupant expectations. Different buildings, different houses, different occupants, they're all different. You may build two houses exactly the same, and they're not going to heat and cool exactly the same. But if they have different occupants, the occupants are often not going to have the same expectations of their heating and cooling system. So we need to understand that. Let's talk a little bit more about that. One of the first things we need to do in order to understand what the occupant expectations are is we've got to start with asking questions of them. Now, if we ask a question that says something like, what do you think of comfortable? Or what do you want in your house? And they say, I want to be comfortable. Then we have to continue going deeper down that road. We have to dig to figure out what they consider comfortable. Because what you consider comfortable and what I consider comfortable may be two very different things. What I consider comfortable, and what my wife considers comfortable, I can say is two very different things. We're different people. Now, we live in the same house and we coexist, so that works. But when we ask those questions afterwards, we have a couple of paths we can take. We can do what happens a lot in our day-to-day lives, which is hearing. It's accidental, it's involuntary, it's effortless. We just hear things, okay? But if we really want to learn what somebody is telling us, we need to listen to them. We need to focus on what they're saying. We need to be very voluntary about it, and it's an intentional piece. We're listening to what they're saying in order to learn what they need so that we can deliver what they need, what they desire, and they have a good outcome in the end, which is good for us as a contractor because then we end up having happy customers, okay? Now, as I said before, comfort is probably one of the biggest things that it's difficult for us to figure out what the customer's comfort level is. What do they consider comfortable? So we have to really dig into that. We got to talk about it. And there's other things that we can do as we're going through this process to improve normal everyday comfort. And we're going to talk a little bit about that. Right? Now, in the end, this is my goal. I want to have a customer that looks at me the same way my dog looks at me. Happy. Just absolutely ecstatic to see me. Happy with the job I did. Happy with their comfort level in the house. That's the goal. Are we going to make that every time? Probably not. But if we don't try to head that direction and we don't try to get customers that look at us like that, we're never going to make it there. So keep on trying. Now, let's take a look at some quick action items here. We want to ask questions, listen with intent, understand desires and expectations, and then we need to communicate with the customer. If they have totally unrealistic desires and expectations, they want to keep their house at 60 degrees in the summertime and they want it 80 degrees in the wintertime. Communicate that maybe those are a little unrealistic. Maybe we might not be able to do that. Or if they do want to do that, they're going to have to put in special equipment because that's outside the normal operating range of a lot of equipment. So keep that in mind. Make sure we communicate back with those customers. All right. Now, having a design process, having a process is a good idea for anything because it keeps us on track. It keeps us from wandering off, going down rabbit holes and squirrel holes and other sorts of holes that we may fall into, trip into, and not come out of for a long time as we go along the way. And I'm quite certain that Bill is chuckling right now because he and I both lament the fact that we do this quite often and we'll go down all kinds of holes and things. And we do have processes in place to try to keep that from happening sometimes. So, we all work on it, whether we're in what kind of business we're in, even in our lives, we have processes, right? So in HVAC, a design process that's often used comes from ACA or ACCA, Air Conditioning Contractors of America. And this guy over here, this is my buddy, Angry Ed. And he kind of keeps us on track here, okay? And he might bring you a message once or twice going through this, all right? So the design process works like this. And they have a series of what's called manuals, okay? These are the residential manuals. This is mostly focused on residential. There is also a set of commercial manuals over here available as well that does the similar thing. So with the residential design manuals, it starts with RS, which is the system concept. And that kind of lays the whole framework for what's going to happen. Gets you a good idea of how things are going to flow, what's going to happen. We step into J. This is a very commonly used manual, sometimes misused, sometimes not fully used, but it's very common. A lot of people know and know the manual J. If zoning is involved, manual ZR is a great thing to have. All right. Then we step into manual T, which is air distribution. When we say air distribution, that is not ductwork. That is air distribution within the room. How are we going to distribute it within the room? We'll talk more about that as well. S is equipment selection. So we want to match, now that we know we have J here, we know what our loads or how much heat the house needs. We have T, we know how we want to distribute it in the room. So where the registers are going to be placed in the room for optimum distribution, right? The supply registers is what we're talking about there. Then we want to select the equipment to meet those criteria, right? Once we have the equipment selected, then we can design the ductwork because we have to know what kind of equipment we're going to use and where our air distribution points are going to be located at before we can design the ductwork to meet those needs. And once we're all finished with that, then we go down here to manual B, which is the test, adjust, and balance. And at the very end, we want to make sure that everything is tested properly. It's working the way we designed it, the way we intended it to work. So we have to test everything when we're done. Right? We want to confirm that we've got everything working properly. All right. So let's go kind of through a few more steps in this. We'll talk a couple things on each step. One of the things that's, I'll say, probably not paid attention to as much as it could be in load calculations, especially on retrofit homes. Now, keep in mind, this is where we're going into an existing house. It's got existing equipment in it. Maybe it needs to be replaced. Maybe it's just getting up there in years and somebody wants to replace it, or maybe it's broken down, needs to be replaced. But an air leakage test on the house using a tool called a blower door helps the load calculation, because then we know how much air is going to be infiltrating into that house. We understand that. Otherwise, we're making a guess. Okay. And if we're not testing, we're guessing. So a house leakage test is a really good idea to help dial in that manual J. Does it have to be done? No. There are guesses. There are options in manual J that you can put in there as standard options without doing that test. But if you really want to try to dial it in, it's a great idea to do that test. Okay. So let's take a look at the house envelope. We look at the blue line on this screen. That's what we call our air sealing envelope, our infiltration envelope. And if we just built that house and it was really, really tight, we got a furnace in here, okay, great. Often that doesn't happen though. What we do in a house is we have that really tight and then we start cutting holes in it. And a lot of times our ductwork goes through that. Not always, but if a ductwork goes through that air barrier, right, now we've created holes in our air barrier. And what we're going to do is we're going to put a fan in there and we're going to create pressure here and pressure here. And if there's any leaks in that ductwork, pressure differential makes air move. That's how we get air from moving to point A to point B. So the fan creates pressure differential inside those ducts. And now we can leak, or we can move air from outside. You know, if this duct down here, being the supply duct, leaks, it's going to blow air into the crawl space, which isn't going to go back into the house. It's going to blow out these vents over here. Okay. Conversely, if our return duct leaks up here in the attic, it's going to pull air into it because it's under a lower pressure than that attic. So air is going to enter from the attic into the return duct. And in this case, this is our air filter. So it's going to come in after the air filter, which is going to make our equipment dirty and blow a bunch of attic dirt right back up into our house eventually. So we need to make sure that our air barrier continues, right? The ducts are sealed to that air barrier, and the air barrier then continues throughout the duct, making sure those ducts are tight. One of the other pieces here is insulation. We try to do a really good job insulating everything up here in the attic on the walls, and then we cut holes in and we move hotter and colder air through those ducts that have typically less insulation, because most of your residential ducts are at best an R8 insulated. And if that gets squished at all, the R value goes away. So to me, air sealing and insulation, a lot of that can actually be done really easily with some of the technology we have today in spray foam, which I love. Just spray foaming those ducts, keeps them insulated, seals them to the house, can do a fantastic job. So that to me is a great option right there. But just keep that in mind when you're looking at a house, because anytime we have leaking ducts or under insulated ducts in unconditioned spaces, we start adding load to that. And you'll see that in Manual J, in the outputs of Manual J. All right. Now let's look in the house a little bit. So we've got a house layout here. Here's our air moving device, our air filter. We got some rooms. We got some bedrooms in here. It's like we got maybe a utility room. Okay, so different rooms and whatnot in the house. A couple bathrooms here. okay? Because we have a central return, all of our air has to come from these supply registers through the door or through an undercut or through some way to get back to our central return. If we don't have a good path for that and we close one of those doors, say somebody wants to go to sleep at night and close their door, we create a pressure differential in this room, okay? And because we create a pressure differential, because we're blowing air into this room, maybe it's not getting back into the house. Some of it may be leaking out of the house. Well, if it leaks out of the house, then it's got to come out and come back in because everything has to equal out eventually. The pressure seeks an equal or pressure seeks a level. So it's going to come back in over here. So we're blowing air out of this room. We're bringing air back in somewhere else in the house to bring it back to the air handler because the air handler is going to move the same amount of air no matter what. Really doesn't care where it comes from. So we'd like to control that. So now we have a pressure differential. Typically, we want to see less than 3 pascals of pressure in a room. That's not a hard and fast rule because it really depends on how big the leaks are. If you have a room very leaky outside, it doesn't necessarily create a big pressure. So it all depends on how leaky that house is and where the leaks are at. All right. Now, this is something that's a really good idea to survey while you're going through. You can take a micromanometer. You need something that reads down in pascals or tenths of a pascal, and read across that door between the house and the door while the door is closed. You're inspecting the house, which we'll talk a little bit more about that. And that gives you that information, and it will tell you if you see pressure in there, you may want to increase the transfer, whether put in a transfer grill, a jumper duct, undercut the door more, something along those lines. So that's a great test to take with a micromanometer right there. All right, let's talk about register placement. Okay, so what we really want to do with registers is we're going to put conditioned air, actually over conditioned air. It's going to be hotter coming out of the heating than we want the room to be. And that warms the air up in the room. But that air does something else. That air then transfers heat out of it into surfaces, which is really the first thing we want to concentrate. That's what we want to focus on heating up because the air, there's enough surfaces in the room that it will heat the air in the room. But those surfaces cause our body to, either heat radiate from that surface to our body, which makes us feel hot, or radiate heat from our body to a colder surface, which makes us feel colder as humans because radiant heat affects our skin quite a bit. We can tell this by how close we stand next to something really cold. If you've stood next to a cold window or a hot window, the closer you get to it, the hotter you feel. Right? That's radiant heat. What we don't want to do is blow air on people. So we need to make sure our registers are placed properly, number one, and number two, that the registers are of the proper type to put the air where we want them. Now, I have had some customers that love air blowing directly on them. It's very, very rare. You can do that. Be careful. That's what I'm going to say. Be very careful if you do that. Okay. As Mr. Ed says here, Mr. Angry Ed, don't blow air on people. The rule is less than 50 CFM hitting a person, and they typically won't feel it. Now, some people may be a little bit more sensitive to that, but again, that's all going to be part of your manual T process. Now, one of the other things is we can use a thermal camera to inspect the surfaces in the house. If we are there when the equipment is running, say in heating or cooling mode, we can actually go in and use a thermal camera to see what the distribution of that air is on the surfaces. If somebody's really uncomfortable in a certain area of their house, we go in there with a thermal camera and we start looking around and we can see hot spots and cold spots. Maybe it's right next to their chair that there's a really cold spot or a really hot spot. Maybe they're uncomfortable sitting in this one spot of their house or a certain room. And that can be, you can find those things with a thermal camera. So keep in mind that's a valuable tool for this process. All right. Now we need to select the equipment. The equipment needs to match. And when we say match, not only does it need to match the conditions that the house needs, but it also needs to match each other because when we're talking about a system, most of the time we're going to have an indoor air handler and an outdoor heat pump. And those two need to be able to work together. And there's rating systems for that, of course, from AHRI and things like that. And if those two don't work together, well, then you may not get the capacity that you think you're going to out of it. Okay? If we're going to go all electric, we need to take a close look at the electrical panel. Right? We need to make sure that there's physical space in there because we may be having extra breakers added. So make sure that there's enough space and or enough capacity. Now, if you have things like 100 amp electrical service and you want to go all electric, there are load shedding options out there that will monitor the loads and they'll be able to help control them, turn them off and on whenever they need them, things like that. So look into those options. I don't know a whole lot about them, but I have read about them and I've seen people demonstrate them. They look like they might work pretty well. All right. Ductwork. We can look at ductwork a lot and we can visually say, okay, we think that's going to work. We think it's not going to work. That's some really pretty sheet metal. But until we test it, we really have no idea whether it's going to work or not. We just really have no idea because of, we're guessing or we're testing. Okay. So there's several ways that we can test this. One of the biggest ways is we need to make sure that the the ductwork is large enough for the new equipment that we're going to be putting in there. Once we do that, the equipment at least is going to work well. All right, and the ductwork's not going to kill the equipment. Now, one of the first things we need to do, if the old equipment is still operating well enough, if we can still move air through it, the blower's still good, we really need to take a static pressure reading. All right. Take your static pressure reading. I'll show you why here in a little bit, because that's going to be able to help you predict what the new equipment is going to work like, especially if you're changing sizes. A lot of times what contractors are finding is that gas furnaces are way oversized and we can get away with a lot smaller unit, which is great for a heat pump. We'll talk about that in a little bit too. But with downsizing, it increases comfort because we don't get that blast of hot air coming out and then off, blast of hot air and then off, which creates hot and cold cycles because the material in the house is constantly losing heat in the wintertime. Okay. But we're modulating the volume of heat with turning that on and then turning it off, turning it on and turning it off. When we average that out over an hour or over a day, yeah, we put in the right amount of heat or the same amount of heat that we lost, but we put it in these spurts. And it's kind of like trying to take a shower with a fire hose, right? We'd like to turn that down a little bit, or watering some very nice sensitive flowers with a fire hose. You don't water them with a fire hose, you water them with a nice gentle mist or a drip or something. You put it in there very intentionally. So that big rush of air, that big hot air coming in there can create a lot of comfort issues. So downsizing equipment, right sizing it to the house can help a lot. And we want to make sure that the ductwork is going to be able to handle that equipment. So static pressure first, external static pressure on the unit, right? And then we want to measure airflow across that unit. One of the easiest ways to do it, that is by using a product called the TruFlow Grid, and the TEC DG8 and the TruFlow Grid work together really well. So that's an invaluable tool for this process. Okay. Once we get done with that, we need to record all that information. This is the friction rate worksheet out of Manual S. This is a really, really handy thing to have. And if we use this properly, this tells us how much static pressure we have left over for the ductwork from all the other components that are in there. So we run that down, it gives us a friction rate or the available static pressure on our from our unit. All right. Now, let's talk a little bit more about airflow in different units. A gas furnace, because there's different efficiencies, things like that. A gas furnace is going to run anywhere from 160 to 370 CFM per 12,000 BTUs. Now, as we know, gas furnaces are typically rated on input BTUs. This value, however, is output BTUs. So per 12,000 BTUs of output, which happens to correlate to a ton of air conditioning, which we know nominal airflow for an air conditioner is between 350 and 450 per ton. So per BTU, our airflow is higher with a heat pump, right? Which means the temperature is going to be lower. The intensity of that heat coming out of it is going to be lower. So if it blows directly on a human, they're going to feel like they're getting cold or cooler air blown on them, right? So heat pump airflow, 350 to 450 per 12,000 BTUs. That's a nominal, but that's the difference between the two. So you can see if we need the same BTUs from a heat pump that we had coming out of a gas furnace, we may have to do something with the ducts. Now, lucky
Hey,
for
Eric,
us, yes,
we
Bill's
have a
got a question.
question. It's from Keith Keller.
Hi, Keith.
Sometimes you can adjust the airflow with the air handler. How do you determine the best fan speed for a system? Where does that fit in your process?
Great question. Coming up.
Coming right
Okay.
up.
We'll get to that in a little bit, and that is, I'll say it's based on the performance data of the equipment. And what that means is you got to get into the performance data, figure out how many BTUs you need and how much airflow that equipment needs to deliver that many BTUs. So that's part of the whole process of looking at that performance data. And that's part of going through Manual S. Now, remember we have our airflow here. We may have different BTU numbers, right? These are just per 12,000. But remember those static pressure and that airflow reading that we took before. Okay, here's an example. We're going to talk about existing equipment. We got a gas furnace, 96,000 BTUs per hour of output. Okay, so that would be a 100,000 nominal furnace, right? 1,370 CFM. Existing 0.7 inches of water column or water gauge is our external static pressure. Now, we did all the work. We figured out that we can put in a much lower capacity unit because the house doesn't need that. This just happened to be what they put in, what somebody put in. Okay. And I can speak to this one because this is very, very close to what my house is. Now, new equipment going in, heat pump and all electric, right? We need 34,500 BTUs per hour of output, all right? To get that, we're gonna run 1,050 CFM through that equipment. And we have a target in mind. We have a target we wanna meet of 1/2 inch of water column external static pressure on that new unit going in. So how do we figure out what's happening now and predict what could happen in the future? We're going to use just a little bit of math, all right? And it looks like this. We need the existing external static pressure, or ESP, right? We're going to take the target CFM, divide that by the existing CFM, and square that value. So in the end, it would look like this, right? 1,050 divided by 1370 squared, 0.78 times that number, which is going to equal out to 0.78 times 0.59. We're going to end up with roughly 0.46, if you see that over here, 0.46 inches of static pressure if we did this. Now, that's pretty doggone good. You know what's really cool about this? This is easy to do. Easy to do. And you don't even have to memorize it. If you know this formula, you do what I do and drop that into a spreadsheet. You enter those three values into a spreadsheet, boom, you got your new number. It's really easy to do. I love spreadsheets. They store my math. That way I don't have to remember it all or have notes somewhere and have it all written down. Okay? So, few action items for success. Follow the process. Gather the information for that process. Make sure that process includes what information you need. Predict the outcome that you're going to have. And above all, trust your calculations. Trust these calculations that you're doing. Trust the calculations that come out of the manuals, as long as you know that you put good information into them. It's like anything else, garbage in, garbage out. If we don't put good information into calculations, we don't get good results out of those calculations. So, looks like we're doing good on questions so far. Bill, thank you for bringing that one up.
Yes, sir.
Okay. Now, let's talk a little bit about equipment operation. It's part of the process is understanding what that equipment is going to do. And that's manual S. We talked about understanding what the equipment is going to do, a little bit about how it's going to operate. When Keith asked the question, and some of this is also looking at how are we going to set up the controls to control this, because it's not just a simple on-off thermostat anymore. Now we have to have multiple stages of controls. What's going to turn on when? How's it going to make that decision to turn on? Things like that. One of the first things I recommend people look for when selecting a heat pump is at the defrost. So when a heat pump is running, the outdoor coil is often below 32 degrees or freezing temperature, even when the air temperature is higher, because we have to make that outdoor coil colder in order to absorb heat into it. So moisture on the air will frost on that coil, and at a certain point, we have to reverse that heat pump back into a cooling unit so it's not heating the house. It's going to take a few minutes, pull just a little bit of heat out of that house, put that heat into the outdoor coil, and melt all that frost off of there, and that frost is going to run away. Okay? That's all controlled by something called a defrost board, right? And there's two basic styles of defrost. There's what's called time and temperature and demand. Now, time and temperature initializes on time. So every 30, 60, 90 minutes or 120 minutes, it's going to go into a defrost cycle. Now, it might only be in that defrost cycle for a couple seconds or maybe a minute because it terminates on coil temperature. So it initiates on time, terminates on coil temperature. All right. The other style is called demand defrost. And demand defrost looks at outdoor air temperature and coil temperature, compares the differential between the two. And when the differential gets to a certain point, then it turns on the defrost. Now, demand defrost typically uses less energy, runs less defrost cycles, because often people will set up defrost cycles to bring on some heat inside the house so that we don't get what's called cold blow onto people if there does happen to be some air blowing at people. If people don't feel like it's cold in the house for a couple minutes while it goes through a defrost cycle. But I highly recommend demand defrost boards versus time and temperature board. All right. Now, this is where we get into knowing a little bit about how this operates. And a lot of times we're going to have, to Keith's earlier question, in a data sheet from the equipment, it's going to have a lot more information in it than this. It's going to say what airflow that's operating at, things like that. But this shows a correlation between outdoor temperature, right, delivered BTUs per hour, how many watts I'm using, what my COP is. Now, COP is coefficient of performance, and that compares how many BTUs I'm delivering versus how many watts I'm putting into to get that work versus how many watts I would be getting if I was running resistance electric heat. So you can see down here at 15 degrees, I'm still getting 2.2 times the amount of energy out. I'm getting 13,000 BTUs out for 1,800 BTUs put in. Whereas if I put that same 1,800 BTUs into electric resistance heat, I would only get a little over 6,000 BTUs out of it instead of 13,000. This is why we use heat pumps, right? Because we can move heat for less energy being used. And even down at 5 degrees, I can still get 9,000, whereas if I was running electric heat, I'd only be getting 5,900. I get 9,800 out of it. So there's still an advantage there to run the heat pump. Now, is the heat pump going to necessarily keep up with the house at that point? Who knows? I don't know until I have a load calculation and I develop something called a load slope. Right? And that kind of looks, this is the first piece of that. And we look at down here, this is plotted the equivalent resistance heat that I would be getting out of that unit, right? And this is my performance slope. This is how many BTUs I'm actually getting out. So this would be same wattage into an electric heat. This is my actual BTUs out running the heat pump. As long as the green line's above the blue line, I'm better running. I should keep that heat pump running because it's going to use less energy, therefore costing my customer less. Right? Same kind of data, right? Same thing, except this is what's called an airflow controlled inverter, where we control the compressor speed of an inverter compressor by changing the airflow indoors. So there's no communication between the indoor and outdoor unit. There's just standard conventional thermostat wires, right? But being as it's an inverter, it carries that 2.2, it's all the way down at 5 degrees. So I plotted them the same, right? They'll run lower than that. But all the way down here at 5 degrees, you see it's the same nominal tonnage unit, but I'm making more BTUs per hour. I am using a few more watts than that single stage was, but I still have good COP out of it. All right. And this is the performance slope on that, again, comparing that resistance electric heat and the performance delivered BTUs of that inverter heat pump. Now, when we're talking about inverters, it's very important to understand they have maximum and minimum. So down here, if my load is down here underneath this line, okay, it's going to be shut off. This is where we can get in trouble with oversizing heat pumps. So I've heard a lot of people say, hey, it's an inverter. I can oversize it. I can do whatever I want to with it. You really can't, right? Got to be careful with that. Because if you get it oversized too much, you end up down here in the operating envelope or the operating range and your units just shut off, and then you might as well have a single stage in there because it's just going to come off and on and off and on. That's going to cause uncomfortable. And just so you know, this happens to be the heating performance curve of a unit, right? It does the exact same thing in cooling. You'll see this is 70 degrees right here, right? My maximum tapers off the hotter it gets outside. My capacity actually goes down. Same thing with my minimum capacity. It's going to go down the hotter it gets outside. That's how refrigerant-based units work, right? It's just kind of showing you what it does on cooling side as well. Now, let's look at this a little differently. So this is my performance line here, that green line again. Again, we're back to our single stage heat pump plus some electric resistance heat. The blue line now, though, is the load slope of the house. This is how much heat the house needs. And this line's actually going to move a little bit depending on the conditions outside. Is it sunny? Is it not sunny? Is it windy? Is it not windy? It's not all about just outdoor dry bulb temperature. A lot of other factors to it. Here's the thing. My performance is dropping, right? Where these lines cross somewhere around probably 28, 29 degrees Fahrenheit outdoor temperature-ish. Okay, and that again depends on what the weather's doing. Is it sunny? Is it windy? Is it nighttime, daytime, cloud cover, no cloud cover? All that goes into that. But roughly around here at 29 degrees, the heat pump in heating mode will no longer be able to keep up with the demands of the house. Okay. Now, if you remember that COP chart, it's still cheaper to run the heat pump down here than it is to run straight electric heat. Now, a lot of people will say, once your heat pump stops heating or loses performance or can't keep up with the house, you should just turn it off and run electric heat. And I can say from experience that's incorrect. Okay. And the first job that I had, my boss had done a house way before I started working there. In and all, he was the only did one house in this new addition. All the other houses were done by another contractor. And the other contractor would tell their customers, hey, when it gets cold out, go over there and switch to emergency heat. Just run your electric resistance heat. Don't run the heat pump. Well, my boss, he understood heat pumps. He understood how to set them up. And he put a special switch on there. And when it got to a certain outdoor temperature, it added in some electric resistance heat while it kept the heat pump running. After several years went by, the power company came back to my boss and said, hey, we've been monitoring this new subdivision, and we know you did the HVAC in this house, and it is running way less. We're using far less electricity on that house. What did you do differently? So he explained it to him. Said, this is how you do it. The heat pump uses less electricity for the number of BTUs. It just doesn't make enough BTUs to satisfy the house. So in this case, now we need to start cycling off and on the electric heat to add some heat on top of the heat pump. We're being additive here. So in here, we start cycling that electric heat until here where it can't, even the electric heat doesn't meet the needs of the house. Then we got to cycle on a second portion of the electric heat to meet the needs of the house. Still using less electricity than if I completely shut that heat pump off, even though I'm using a little bit of electric resistance heat. Again, that's where knowing how to set up the controls is a really important thing, and figuring out this is really simple plotting. Put the performance numbers into a spreadsheet program. You too can plot this stuff. It's
Hey,
pretty
Eric,
simple. Yes, sir.
got a question. No one's asked it except me.
All right.
Um, Location. Can you put a coil over strip heat? Does it have to be before strip heat? Might it require reconfiguration of the ductwork?
Coils go before strip heat. So when you're additive, just like it is on this graph, we take it up this far with the heat pump, and then we add on with the electric strip heat after it. That's all part of the air handler configuration. So the strip heat is part of the air handler, or is an accessory that goes inside an air handler typically. So not any more reconfiguring of the ductwork than just mounting the air handler in there. Did that answer the question?
Thank you. I knew the answer, but I just wanted to bring that point out.
Excellent. Thank you very much. All right. So a little different. This is with that inverter we talked about earlier, right? It's the air capacity controlled. Remember, it had a flatter slope. So I could take that down to say 15 degrees on this house before I've got to bring on a little and start cycling my electric heat off and on. So just shy of 30, about 29 for the single stage, or maybe 16 on my calculation for this one. Now, we don't spend a ton of time, at least in my environment, we don't spend a ton of time down here below 15. So this probably isn't going to add much cost to electrification or to going all electric. So again, understanding the operation, and this helps to select if your customer is concerned about electrical usage or they're concerned about comfort, things like this can help. Okay, understanding and visualizing how that equipment is going to work, that gives you an understanding. That means you can talk intelligently to your customers so they understand as well. All right. This is an example of a cold climate heat pump. So our scales changed a little bit down here. Now we're going all the way down to -10. Okay. Same slope on the house. All right. And this is the heat pump minimum capacity line down here. So that capacity can vary anywhere in between here. So all the way down to about 40 degrees, that heat pump's going to be cycling off and on periodically. Once that outdoor temperature hits 40-ish degrees, that heat pump should just ramp up slowly and run almost 100% of the time. It might cycle off once in a while, but it should run almost 100% of the time at the minimum speed necessary to condition that house. And that's the way they're designed to operate. Okay. So once we get down here, it should be running 100% of the time. And you'll see I've got 100% performance on that heat pump down to 5 degrees Fahrenheit. Then it starts to go down, and I wouldn't lose heating on my house until around probably -3-ish degrees. Then only then might I have to come on with a little bit of electric heat if you want to, or if you're in an area that the design temperature is up here at 5, I wouldn't put I wouldn't put any electric heat in that probably, or at least I wouldn't turn it on, because I might tell them, hey, or communicate to them how they want this set up, talk to them about it, say, are you okay if it goes down, below zero, if your house temperature drops just a little bit? It's not going to go freezing, but maybe if they keep it set at 70, it might droop to 68 or 66, something like that. They may lose just a little bit. Okay, fine. If they're happy with that, you don't have to turn that electric heat on. Okay, so different options, understanding what your customer's comfort level is, then understanding what the equipment is capable of, and then how to set that up. Those are all parts of this. Now, this is a dual fuel system. Okay, with a dual fuel system, we want to understand where that really crosses. And I could probably run it right down here to about 30 degrees. But one of the challenges here is this range right here, this 5 degrees before the heat pump performance line crosses the house load line. It can run a lot, which is really, really comfortable. There's no cycling off and on basically of the equipment. The house is really, really comfortable then, because the heat pump is providing almost continuous heat to that house where the house is losing continuous heat. And this is actually something that happened to me personally in my house one time where I had a dual fuel. Anytime my heat pump would turn off, right, and my gas furnace would come on, I would be uncomfortable in the house because my runtime went from almost 100% to maybe 50%. Maybe it was 60% runtime until my temperature went way down here. So my comfort level decreased a lot, right? And then there was this, and we kind of had that dividing line. Oh, I'm nice and happy and comfortable. Hit that line. Angry Ed's over there staring at me like, what did you do? And why am I not comfortable? So we got to know where to set that. One of my solutions was I actually backed that transfer up a little bit because I had it set hard on that performance line. Back that up a little bit so that the gas furnace would transfer a little bit sooner. And I didn't have that hard cliff essentially hitting that. So a little bit different, couple ideas. If you're going with dual fuel, this may be a concern. You may also want to look at a 2-stage to where it kicks down here to second, and then it's running first stage a lot, and it's cycling second stage off and on. But you've got to get a small 2-stage sometimes, depending on the load of the house. But because all these are known, We can predict all these beforehand. We can say, this is how it's going to work when I put it in, right? So understand your equipment performance, know how it works, select your controls appropriately to match with the equipment and with the customer's desire. We need to understand both of those. All right, let's talk about installation. So when we're talking about installation, this is the first thing that happens to new equipment. It sets the tone for the rest of that equipment's life. Couple of really good installation practices. On refrigerant line sets, especially on mini splits or ductless units where we're flaring line sets, do not use the factory flares on those lines because they're not actually a flare. When the factory ships those copper lines out to us, they put a nut on the end of the line and they press down and they push that copper out just enough to hold the nut on and keep the nut from falling off, the flare nut that they ship with the line. That's not a good flare. We need to cut that off, reflare the end of that line with a good smooth flare, and then put it together. Because otherwise, we're going to end up with leaks. Okay. And if you notice over here, right, there's two pieces of copper. This one here on the left, that one right there, I flowed nitrogen through. Okay. The one on the right, I did not flow nitrogen through when I brazed the joint in that copper line. This is literally the difference. All of this black oxidization in here will flake off inside a refrigerant system and end up somewhere. Maybe it ends up in the filter dryer, best case scenario. But it's got to flow through other components. It's got to flow through the compressor. If you ever get a chance to feel this, it's gritty and it's abrasive. Well, the compressor has bearings in it and there's oil in the system. And that means that this is going to wear bearings out, which isn't great. Okay. It's going to clog up dryers, may clog up TXVs, can do all kinds of stuff. But it may not happen for a few years. It may take a couple years for that to show up if this is floating around in the system in small amounts. So good idea, best practice. Follow good installation practices. Make sure you're following the manufacturer's pressure test directions, okay? In general, follow the manufacturer's installation guidelines, but this is something that this is a corner that gets cut a lot. So I'd like to highlight this. So make sure the pressure test is done correctly and get your vacuum as low as possible. The refrigerant system is something that's not easy to repair on a heat pump, so we want to make sure that everything inside that refrigerant system is done correctly the first time. All right. Now, this is the result, and this is actually Bill's house, of a cracked flare. His heat pump froze up, not frosted. This is hard ice. If you ever see hard ice on the outside coil of a heat pump, you got a problem. It should only ever be frost that can be removed with a defrost cycle, right? So they didn't properly flare the lines. The leak happened actually in the wintertime and allowed moisture into the system, which destroyed the refrigerant oil, and the solution ended up being that he had to have a completely new system put in. New outdoor unit, new lines, new indoor coil, because all of them had contaminated oil in them. That can get expensive, okay? So if we take a couple steps to minimize those things in the beginning, we don't end up with situations like this, because let me tell you what, the customers aren't happy when that happens. Are they, Bill?
Sorry, looking for the unmute button. No, they are not. They are not.
They're not happy, not at all. Okay, so a little bit, that's just kind of a great little story that I like to tell because it really highlights what happens if you don't follow it. Now, physical placement is a really, really big consideration with heat pumps. Couple things on placement. One, look up. If there's an eave or an overhang or anything else that can drop things on top of that heat pump, don't put it underneath that. All right. Now, something else that occurs with a heat pump is that it does make a little bit of noise, especially at night, especially when it goes into defrost. So if you happen to look around the house, look on the outside of the house, figure out maybe where you can put it, and then go look inside the house and figure out what's on the other side of that wall. Because if you stick this thing out in your backyard or out in a yard around a house, it's anywhere near a bedroom at nighttime, I promise you, you're going to get a phone call in the middle of the night, maybe, but definitely the next morning, the first time that thing goes into defrost in the middle of the night outside the owner's bedroom, or maybe outside their kid's bedroom. Maybe they don't care about their kids, but definitely don't put it outside the main bedroom of the house where the owners are sleeping at. They're going to be grumpy with you, unless of course they work all night long, and then they'll be grumpy with you in the daytime. But just a note of caution, right? It happens. All right. Make sure that there's, duct work is up to par, that everything's insulated, well sealed. Maybe take out the Bermuda Triangle of duct work here if you see that. But again, you can test it, see how things are working, whether or not. But if there's problems, recommend getting them replaced to the customer. Right? When we're putting in new equipment, one of the biggest pieces that we can do to improve the system, so it improves the dirt catching capacity. We're going to lower static pressure, which is great for motors, great for efficiency, great for noise, is to replace our 1-inch filters. Sometimes they're like this, they're inside of a furnace, things like that. Get that 1-inch filter out of a system and go with larger size filters. Go with something that is bigger, go with bigger drops that are close to the equipment. There's really low hanging fruit to put in things like this when we're in there doing something, because it helps the longevity of the system and really improves things. Installation location, things around the unit. Do we have things that are growing up around the unit? Is there physical space to put the units in place? What about maintenance? All things we got to look at. Okay. Do we need to replace wiring? Do we have to put in different disconnects, running new refrigerant lines? All these things we got to look at when we're looking at the location of equipment. We also need to consider how we're going to get them up, right? This is great. This is how we want heat pumps. We want them sitting up off the ground. A lot of the reason for that is because of the water that drains off of them when they go through the defrost cycle. Because if that builds up in the bottom of this cabinet, if it's allowed to build up in the bottom of that cabinet, it creates hard ice or clear ice, and it will eventually build up far enough that it will freeze and break the bottom passes of the refrigerant coil. And then you have a leak of refrigerant in the middle of winter, and the owner's not real happy because you probably just destroyed that unit because it's not up on pump ups. It's really easy to put them up on what's called pump ups or legs, and we also need to make sure we get them up above the snow line, because we don't want our snow stacking up in front of the fans anywhere up beyond the bottom of that unit. If we have an updraft unit like this one, we don't want that snow coming up in here and catching and holding water in the bottom of there. Okay. Auxiliary devices. A lot of these units, especially if we're doing inverters, variable speed things, have electronics in there. It's important to protect those electronics. So something simple as surge suppression, a device like that, or like this one, has a built-in voltage monitor on it, as well as surge suppression. It's got a contactor in there that it turns the equipment off if it gets high voltage or low voltage. And it monitors for spikes and tells you what we get for spikes. So it's really just a little bit of extra protection for the equipment, just like we do for a lot of our TVs and appliances and things like that. We're plugging them into an outlet strip with a surge protector in it. Well, that's the surge protector for your equipment with a little bit of extra on it, because over voltage and under voltage can also damage the motors and the electronic equipment in there in certain cases. So really great thing to add on. All right. Action items. Follow your good installation practices. Make sure those are getting done. Select your equipment location thoughtfully and do that well. Make sure you're putting on any ancillary devices that need to be put on. Think about those, what's going to happen in this certain system or this certain geographical area. Get those ancillary devices on. Maybe that's a stand to get it up, anything like that. Now, we want to communicate back to the customer. Okay. Frosted over coil. If you've ever owned a heat pump or you've ever seen one defrost, you know what I'm talking about in the wintertime. If you haven't, the first time you see a heat pump defrost and it comes back on, it looks like the unit's on fire because it's spewing water vapor out of the front of it when it turns the fan back on after it's done defrosting. I can have gotten a lot of calls over the years when I was working for contractors. Yes, sir. Can you come out right now? That new heat pump you put in, yes, it's on fire. No, your heat pump's not on fire. That's a defrost cycle. And the customer understanding that was on us as the contractor because we didn't properly explain it. So make sure we're properly explaining that your customer understands. It's going to run in the wintertime. It's going to make a puff of steam when it comes out of defrost. And that's perfectly normal. Right? Make sure you're selecting a good control system. Our control systems are not simple on-off anymore with this, right? They're going to have a couple extra settings in them. So make sure you're selecting a control system that does what you want it to, has the control logic, and works with the equipment that you're putting in. Okay? Now, make sure your controls are set up the way to operate the way that you designed it. And then communicate to the customer. Communicate how the system is going to operate and communicate how to operate the controls. Walk them through it. Have them, as you're walking them through it, have them do the actual operations, not you. Just tell them where to press and what that's doing. Make sure they get it. Okay. A couple other useful resources, and then we'll be wrapped up for the evening here. ASHRAE Standard 55, Thermal Environmental Conditions for Human Occupancy. Great little document to understand the indoor thermal environment, right? To keep people comfortable or as comfortable as possible. Okay. ANSI ResNet ACA 310 2020. This one's more for new buildings, but it can be useful if you want to use the process in it for grading installation systems of HVAC systems. Or you can use ASHRAE Standard 221, which is a method to measure and score the heating and cooling systems and their performance. Right? A couple other things. Thermal Comfort Principles and Practical Applications for Residential Buildings from Robert Bean. You can find out more about that on healthyheating.com. And Allison Bales of energyvanguard.com has a book called A House Needs to Breathe, or Does It? It's a really great resource. We actually sell that one on TruTech Tools. You can find that on our website. Okay. And if we do all of this right, we get Mr. Happy James here. And he's all good. And he just looks at you adoringly, gives you great reviews, recommends all of his family and friends because you did a great job and their house is really, really comfortable. Now, all the questions.
I'm not seeing any questions. People are just absorbing all this.
Wow.
Tom Leck said, this episode is definitely getting saved and put into my favorites in HVAC.
It's been an honor, sir. I appreciate that. Appreciate you being here watching tonight.
Well, I guess we could wrap it up. I don't see anything else coming in on YouTube or on Zoom. And drop us a line here. Keith Keller says, thank you both. Well, you're welcome, Keith.
Thanks, Keith.
Hope to see you
Thanks
soon.
for being here.
And I think we're all set here. Eric's email is eric@trutech.tools.com.
No,
he's also
no. Don't send it to, that's
it
the
isn't.
other Eric.
That would be a mistake. It's E. Kaiser, right?
There you go, E. Kaiser.
EKAISER@TruTechTools.com.
Yeah.
And Eric's also very active on LinkedIn, and very active on Facebook groups. Also is one of the co-hosts of the HVAC Grapevine, which is a live stream on Sunday evenings at 9 p.m.
Yep, 9 p.m. Eastern.
Yep. So
Yep.
a lot of great ways to interact with Eric, and thank you, Eric, for doing this, and thank you everyone for listening in. Uh, Doug Crowell says, I missed the first half. Can you recap? Doug, it's recorded on YouTube.
You'll have to go back and rewind it,
Yeah, you're
Doug.
gonna
I'm
have to
sorry.
rewind, and you can even watch it a little bit faster, like 1.25 speed.
Yeah.
Cindy's Ice also says, thank you guys. This was great. We appreciate everyone who listened in tonight, and we're gonna
Thanks,
close the
Cindy.
recording out. Okay. Take care, everyone.